In mathematics, separation of variables is any of several methods for solving ordinary and partial differential equations, in which algebra allows one to rewrite an equation so that each of two variables occurs on a different side of the equation. Ordinary differential equations. Suppose a differential equation can be written in the form which we can write more simply by letting, as long as h0, we can rearrange terms to obtain, so that the two variables x and y have been separated. Dx can be viewed, at a simple level, as just a convenient notation, which provides a handy mnemonic aid for assisting with manipulations. A formal definition of dx as a differential is somewhat advanced. Alternative notation. Some who dislike Leibniz's notation may prefer to write this as, but that fails to make it quite as obvious why this is called separation of variables. Integrating both sides of the equation with respect to we have or equivalently, because of the substitution rule for integrals. If one can evaluate the two integrals, one can find a solution to the differential equation. Observe that this process effectively allows us to treat the derivative as a fraction which can be separated. This allows us to solve separable differential equations more conveniently, as demonstrated in the example below. As in, because a single constant is equivalent, example population growth is often modeled by the differential equation, whereas the population with respect to time is the rate of growth, and is the carrying capacity of the environment. Separation of variables may be used to solve this differential equation. To evaluate the integral on the left side, we simplify the fraction and then we decompose the fraction into partial fractions, thus we have let. Therefore, the solution to the logistic equation is to find let in. Then we have noting that, and solving for a, we get partial differential equations. The method of separation of variables is also used to solve a wide range of linear partial differential equations with boundary and initial conditions, such as heat equation, wave equation, Laplace equation and Helmholtz equation. Homogeneous case. Consider the one-dimensional heat equation. The equation is the boundary condition is homogeneous. That is, let us attempt to find a solution which is not identically zero, satisfying the boundary conditions, but with the following property. U is a product in which the dependence of U on x, t is separated, that is, substituting U back into equation and using the product rule, since the right-hand side depends only on x and the left-hand side only on t. Both sides are equal to some constant value minus lambda. Thus, and minus lambda here is the eigenvalue for both differential operators, and t and x are corresponding eigenfunctions. We will now show that solutions for x for values of lambda 0 cannot occur. Suppose that lambda less than 0. Then there exist real numbers b, c such that from we get and therefore b equals 0 equals c, which implies u is identically 0. Suppose that lambda equals 0. Then there exist real numbers b, c such that from we conclude in the same manner as in 1 that u is identically 0. Therefore, it must be the case that lambda greater than 0. Then there exist real numbers a, b, c such that and from we get c equals 0 and that for some positive integer n. This solves the heat equation in the special case that the dependence of U has the special form of, in general, the sum of solutions to which satisfy the boundary conditions also satisfies n. Hence a complete solution can be given as where dn are coefficients determined by initial condition. Given the initial condition, we can get this as the sine series expansion of f. Multiplying both sides with and integrating over 0, L. Result in this method requires that the eigenfunctions of x, here, are orthogonal and complete. In general, this is guaranteed by Sturm-Liouville theory. Non-homogeneous case. Suppose the equation is non-homogeneous, with the boundary condition the same as expand h, u and f into where hn and bn can be calculated by integration, while n is to be determined. Substituting back to and considering the orthogonality of sine functions we get, which are a sequence of linear differential equations that can be readily solved with, for instance, Laplace transform, or integrating factor. Finally, we can get if the boundary condition is non-homogeneous, then the expansion of n is no longer valid. One has to find a function v that satisfies the boundary condition only, and subtract it from u. The function uv then satisfies homogeneous boundary condition, and can be solved with the above method. In orthogonal curvilinear coordinates, separation of variables can still be used, but in some details different from that in Cartesian coordinates. For instance, regularity or periodic condition may determine the eigenvalues in place of boundary conditions. See spherical harmonics for example. Matrices. The matrix form of the separation of variables is the Kronecker sum. As an example, we consider the 2D discrete Laplacian on a regular grid, where n are 1D discrete Laplacians in the x and y directions, correspondingly, and are the identities of appropriate sizes. See the main article Kronecker sum of discrete Laplacians for details.